Well, thank you very much to the organisers for inviting me to this wonderful meeting. It's fantastic to see just how much as so many subjects have moved on. As Simon has just presaged, I'm going to expand a little bit on the way that we're making these rubidium-cesium molecules, because it's quite general and a different way from the magnetoassociation that we've nearly always used up to now. I'm going to skip most of my motivation because we've had it pretty much all of it already. So Gabrielle's told us about the sodium cesium molecules made in Kang-Kuen Ni's group. Simon's just told us about the RbCs molecules made in Durham, both in tweezers. And there are, of course, other experiments such as John Doyle's experiment, where they pluck laser-cooled calcium fluoride molecules out of a moth and do wonderful collision experiments with them. The purpose of this talk is to describe what we call mergoassociation. And what's novel about it is that you don't have to do anything except merge the tweezers, and you magically form molecules. So before I move on to RbCs, where this does happen, I'm going to say a little bit about sodium cesium, where it doesn't happen, to set the stage and allow us to make the comparisons. So before we were working with Simon on rubidium cesium, we were involved in some aspects of Kang-Kuen Ni's work on sodium cesium. Just for clarity, we do theory. What have I done? There we go, it's okay. So they take tweezers containing sodium and cesium, they merge them to form a confined pair. Actually, one of the first measurements they did was to measure the binding energy of the least bound spin stretch state, which is a pure triplet by Raman spectroscopy. So going from the atom pair in the tweezers up and down again to this least bound state of the pure triplet potential. And that's an extremely valuable measurement for working out what the interaction potentials are. Largely we do interaction potentials. They then moved on to locate Feshbach resonances, and particularly they located not the only Feshbach resonance they found, but for absolute ground state atoms, they found a Feshbach resonance near 864 Gauss, which Gabrielle's mentioned to us. And they made molecules by magnetoassociation. Now that's pretty much where we came in. We used those measurements of those two things plus some others, to fit key parameters of the interaction potentials, basically improving on and modifying and improving on some pre-existing potentials from Eberhard Thiemann's group. And having done that, we used our potentials to calculate the near threshold levels. And this is the kind of diagram that we often like to show. The black lines are rotationless states, S-wave states. This dashed line coming down here is the ground state of sodium plus the ground state of cesium. The particular resonance at which they make molecules is here. But what they do for magnetoassociation is basically start from atoms just above the resonance, sweep down and come into this bound state. And that's essentially exactly what you do in the gas phase. So there's nothing different about the making molecules in these molecules in tweezers. And having got this understanding of the interaction potentials and the energy levels, they were then able to go on and do all sorts of other interesting experiments, some of which we were involved in, most of which we weren't, to get down to the ground state and do the wonderful things that Gabrielle was telling us about yesterday. Anyway, so now moving on to rubidium cesium, the idea was that we would just do the same thing. we would take rubidium and cesium. Well, no, before I say that, for rubidium cesium, we knew a lot already because we've made molecules in the gas phase. So both in Innsbruck and in Durham, we've been making molecules since shortly after 2012 or thereabouts. We made the molecules by magnetoassociation. So here's another of these energy level diagrams for rubidium cesium. In this case, the lowest state of rubidium plus the lowest state of cesium is horizontal. We've shifted it to be horizontal at 0. And there's this bound state that runs across here that's bound by about 120 kilohertz or something, and various steeper states crossing it. And of course, they have avoided crossings both with the thresholds and with one another. So the usual experiment for rubidium cesium is to start with atoms somewhere around 200, 205 Gauss or thereabouts. So not the red line, but you're actually at the just above the 0 point. Sweep down, go over an avoided crossing here to make molecules here, and then play around. But normally you come down and you do stirap to the ground state from here. So we thought we'd do the same thing in tweezers. Simon's group thought they'd do the same thing in tweezers. So they made rubidium and cesium atoms in separate tweezers near the top of this, near the 205 Gauss or so, cooled them to the motional ground state, merged the tweezers, and we imagined that what was going to happen was exactly the same. When we sweep the magnetic field down, so they actually measure the binding energies of these things, but what we expected was that we were going to find molecules in these, basically the blue points. Those are the gas phase points, but we expected to get the same thing in tweezers. That is not what happened. What unexpectedly, they found that the molecules were following this path. They were quite quickly coming down to much more deeply bound states. So instead of the blue ones, which are the ones we would have got in the gas phase, we got molecules in these deeper bound states. However, if they merge the tweezers at 197 Gauss, which is below 197 Gauss, then they did find the molecules in the blue states. So what's going on? Well, the only explanation of this is that molecules were already in the molecular state as soon as you merge the tweezers. And instead of coming over this avoided crossing along here, you follow the lower part of this avoided crossing. You come down, there's this new G state we found down here, and you map out all these states. That just says what I said, so never mind. On the other hand, when you merge the tweezers below 197, you've again already made molecules. You've done the same thing as you would have done if you'd swept the field across the resonance, but you haven't. So you end up in these states and come down here. Okay, so how does this work? So there's a paper by Ivan Deutsch's back in 2003, which actually sets out it wasn't quite with this application, but sets out the general theory of how this works. If you consider two harmonic traps and they're separated by some distance, which we'll call R0, actually the motion of the atom pair can be separated into center of mass motion and relative motion in the same way as Florian was talking about. And that separation does actually work for separated traps, not just for two atoms in the same trap. And what we're going to be doing here is so Florian was the center of mass, motion of the center of mass was crucially involved in what Florian was talking about. But here we're going to deal just with the relative motion, the separation between the two atoms. And the potential for that has basically two wells. It's got a well at very short range, which is the molecular well. But then there's also another well at long range, which is due to the fact that there are two tweezers, and that's how far apart they are. So the total potential is the sum of these two bits. And this outer one we can approximate it as purely harmonic. Now, the molecular state, however, is sitting off here at very, very close to zero. And clearly, if all you had was the harmonic well, the molecular state would be sitting in the outer reaches of the harmonic well. And so it would be shifted by the value of the harmonic well out here somewhere. So the molecular state is shifted proportional to the square of the distance away from R0. In other words, it's got an energy term proportional to R0 squared. And what that means is that you can tune the energy of the molecular state until it's exactly degenerate with the energy of the atom pair. So that's what's shown here. In this case, the molecular state has been tuned here to be exactly degenerate with that one there. But of course, these two can talk to one another by tunneling through this barrier. So because of the tunneling, that becomes an avoided crossing. So here we have what the energy levels actually look like in the RbCs case. Bound state bound by about of the order of 100 kilohertz when the tweezers are unseparated. Increasing in this is the molecular state, increasing quadratically in energy as the dashed red state. And then we have atom pair states here, but the atom pair states have avoided crossings with the molecular state all the way along. So if you simply take your two atoms in well-separated tweezers out here and bring the two tweezers slowly together, you adiabatically follow this and you end up with molecules. No magnetoassociation involved. It would work for two argon atoms in principle. Just notation, we like to think of this as a 2x2 interaction with a matrix element omega connecting the molecular state to the trap state. So the separation between them is 2 omega. What we do numerically is actually to find these energies, by a method I'll say something about in a moment, and say, okay, that separation is 2 omega. So that's an effective matrix element. So, just to give a little bit of theory, here's our diagram again. The total potential for relative motion is the usual molecular potential V int plus a harmonic potential, but the harmonic potential is separated at R0, the separation of the two traps. When you expand that, well, first of all, the harmonic trap is, this is several hundreds of nanometers away at the place that you're most interested in. And this thing has a minimum at like a few angstroms, 10 Bohr or less. So it's a fairly good approximation just to represent this by a contact potential, a zero range potential, something proportional to the scattering length. So the calculations I'm going to talk about have actually done that. There is no reason why our computational method has to do that. Our computational method can work perfectly well for real potentials. But we do a couple channel expansion. We choose a z-axis that lies along the line that connects the two traps. And under those circumstances, if your traps are spherical, which we assume to begin with, then the whole potential is cylindrically symmetrical around the z-axis. And the trap part of the potential just looks like this. I mean, it's got a small shift, because that R0 is a constant at the moment. It's got a quadratic term in R, and it's got a very, very simple anisotropy. And this gives us an extremely simple set of coupled equations that we can solve to find the bound states. So we expand the wave function just in Legendre polynomials, and we solve some coupled differential equations. I'm going to leave that, but if anyone wants to ask me about it later, I can explain that in much more detail. The beauty of it, with what we can do is that we can calculate the whole energy diagram, but more specifically, we can calculate the avoidedness of the crossing. And we find that the avoidedness of the crossing depends on the harmonic length. This is the harmonic length of the trap. And so you could express it in terms of the trap frequency if you prefer. But basically, it's decaying roughly exponentially, in fact, quite close to exponentially, with the harmonic length of the trap. And having done that, we can combine the calculated omega with the experimental speed of merging and use Landau-Zener theory. I will just point out that Landau-Zener theory involves omega squared, which will be relevant later, but then we've got a velocity, and this is just the difference in gradients between the atomic pair state and the molecular state. We can apply Landau-Zener theory, and we can compare the probability of forming molecules by mergoassociation with what it gives. The red and blue dots are, well, red is the molecules formed by mergoassociation. The ones that aren't formed by mergoassociation do actually undergo magnetoassociation, so those two things are complementary. But the lines are the Landau-Zener theory based on our calculated crossing strength. So it's working remarkably well. The uncertainties come from the uncertainty in the experimental parameters, not from the uncertainty in the theory at this point. Actually, it works ridiculously well. I mean, we've assumed that these tweezers are spherical, and real tweezers are not spherical. They're a long, long way from spherical. In fact, the ratio of the radial and axial tweezers, they're cigar-shaped, and the ratio is about 6. So why did that work so well? Well, we generalized the theoretical treatment to handle, so what we've got is 2 cigar-shaped tweezers like this, and they're being brought together that way along their short axis, if you like. So we generalized this theory to handle general aspect ratios. We like to define the aspect ratio. I think of an aspect ratio as a ratio of lengths, so we define it in terms of the ratio of the harmonic lengths, but you can define it, the square of it, in terms of the harmonic frequencies, if you the other way up if you want. So in general, what we've got is that we've got a molecule at the origin with some potential defining the molecule, and then shifted away from that, we've got this harmonic trap, which is not spherical, and in fact may not be along the z-axis either. It may be shifted away from the z-axis, because experimentally you may want to do that, but you may end up doing that. You may basically have alignment problems in the experiment, so it's nice to be able to handle that aspect of things. We still use a similar coupled channel method. The symmetry gets lower, the basis set gets bigger. Again, we don't need to go into that. But what's important is that the energy level becomes quite a lot more complicated for a non-spherical tweezer. So here we've got the thing that's got 1 unit of excitation in the tightly bound direction, but actually because we've got such a very anisotropic tweezer with a much more weakly bound direction in it, you can get up to 6 quanta of that weakly bound one before you get to 1 quantum of the strongly bound direction. But qualitatively, the same thing is happening. This state, you can come in on this state and adiabatically come down here. It's not really true anymore that the crossings don't interfere with one another. So you know, the numerics are trickier, but doable, and we can solve this again perfectly accurately using our bound program. So we calculate this. If we calculate this crossing strength, this effective matrix element, as a function of the aspect ratio, so 1 is spherical, 2.6 is roughly experimental, we find the rather remarkable result that an aspect ratio of 2.6 is coincidentally really quite close in crossing strength to an aspect ratio of 1, but it's a fluke. We're on opposite sides of a maximum in the crossing strength, though we were just lucky that the theory did so well the first time round. Actually, analytically, we have a sort of semi-analytic approach to this. This maximum is pretty much at root 2, which means across the optimum aspect ratio, the optimum aspect ratio of your two trap frequencies is 2. Now, I don't think I'm going to talk about the approximate method. I will just say, I think, that we have an approximate basis set method based on, as I say, undergraduate level quantum mechanics with a really simple basis set, which gives quite amazingly accurate results. So the blue line here, sorry, the black line here, which you can't barely see because it's underneath the dashed blue, is the exact result from coupled channel calculations. The blue is a decent sized basis set from our undergraduate level quantum basis set approach. The orange is a slightly smaller basis set. And if we even go to the limit of just 2 basis functions, okay, the energies are useless here, but in terms of the strength of the crossing, even the simplest possible 2 by 2 gives a reasonable approximation. And the 2 by 2 we can do analytically. And we come up with a very simple expression for the crossing strength, this omega, which basically AX and AY are just aspect ratios. AA is a thing that's like an aspect ratio, except that it involves a scattering length divided by the trap. And so this gives us a very nice way to check whether to see whether mergoassociation is going to work for a test molecule that you're interested in. I think I've written it down, but I don't seem to have done. Yeah, okay. So that then brings us to the last question I want to address, which is, okay, this worked for RbCs. Why did the Harvard group not see it for sodium cesium? So the probability of molecule formation depends on something that goes as e to the minus, I wrote it down in more detail earlier, but the square of a matrix element divided by a denominator with a velocity in it. That's the Landau-Zener formula. But actually, this omega squared itself turns out to depend very nicely exponentially as the binding energy divided by the trap frequency. So the criterion to get a decent strength of avoided crossing is simply that your binding energy must not be enormously greater than your trap frequency. Now, if you've got a factor of 6 between your binding energy and your trap frequency, this probably ain't going to work. But if you've got a factor of 2, yeah, okay, probably doable. The limiting factor is always going to be, for a given molecule, the limiting factor is going to be how big a trap frequency can you get. You need to approach your molecular binding energy with the trap frequency in order to get this to work. But there's quite a large class of molecules for which that has a chance of working. So the bottom line is that the binding energy for sodium cesium was too high for Kang-Kuen Ni's group to see this, but the one for rubidium cesium wasn't, so Simon's group did see it. So just to conclude, mergoassociation is a new way of making molecules out of atoms, specifically when you merge tweezers. It can work even for systems that don't have any Feshbach resonances or no good Feshbach resonances. It would work with no Zeeman effects at all. So it provides access to a new range of ultracold molecules that you couldn't make otherwise. It does usually require a weakly bound state, so that means it's likely to need large positive scattering limits. It's been demonstrated here for tweezers, but there's no reason why you couldn't make it work for transport in an optical lattice instead of tweezers. And something we're trying to think about at the moment is how easy this will be to extend to things that are not just pairs of atoms, atom-molecule systems or molecule-molecule systems. More generally, atomic optical tweezers provide a powerful way to study atomic and molecular interactions and collisions. And of course, they have lots of possible applications in quantum science. Finally, just to thank some of the people involved, the person mostly responsible for this work is Robbie here. He's also hiding somewhere in this picture. This was a party in my garden when we had a few visitors. Earlier in the year, so representatives of many different cold molecule groups hanging around in this picture. So, thank you very much.
Thank you very much. Other questions? From the back.
Yeah, thank you, Jeremy. Yeah, we heard this morning from Florian about these confinement-induced resonances, and this looks to me like it's somewhat similar. So could you comment on the relationship between these two things?
Well, Florian and I have been talking about this and haven't got to the bottom of it yet. His method, his resonances crucially involve coupling between the center of mass motion and the relative motion, which this doesn't. And of course, his system is unconfined in two of the directions, and he's tuning something other than the distance between them. He's tuning the trap frequency. So I'm trying to think at the moment whether we can generalize. Robbie is in the middle of trying to get coupling between center of mass and relative motion working, but it's not working yet. So watch this space, I'm afraid, is the best I can do.
No more questions.
Yeah, can you hear me?
Yeah.
I don't know whether that's a valid question, but if you do the opposite, so you unmerge, would rubidium go into the left well or right well, or is it a superposition maybe? Would that be useful?
I haven't thought about reversibility of it and where they end up in that respect. The two, I don't know. Going to have to think about it. Interesting question.
Another question over there.
Would this technique also work to create field-link molecules if you have a field-link bound state available?
My intuition is that the answer is yes. However, there is a complication, which is that if your traps are genuinely harmonic and both of them affect both species equally, then the sum of the two traps is always in the middle and doesn't separate. Now, of course, real traps aren't like that. They're more like sort of inverted Gaussians or something. So that problem doesn't really exist when you separate two tweezers, but it does exist at the distances where this crossing as it currently stands happens. So I think it absolutely would work for things like for more complicated particles. Whether it will work for identical particles that are equally trapped by the same, where each one feels the same effect of both lasers, that I'm less certain about.
Okay, if there are no further questions, thank you again.
Thank you.
And close the discussion.